So the last week we learned about the PN junction, and this week we will learn about the diode. But before learning about the diode, I was thinking that the part I learned before is not improving now, because when I'm listening to the class of new class, there was some stuff I couldn't understand it well, so I wanted to improve myself, so I will start to telling the detail from the degenerated semiconductor. So if I start with it, degenerated conductors means like we talk about the doping, and we learned about dopant and then it can be changed into p-type or n-type, as we know. And the degenerated semiconductor is like heavily doped, and so heavily doped, we call it degenerated semiconductor. And the degenerated semiconductor we learned about it is that as we heavily dope the intrinsic semiconductor, and it can turn we can say degenerated semiconductor, and it means that the conduction band level, energy level can be changed. Usually, if it's doped, the energy level is discrete, so it can just stay in a certain level. That's between the energy band gap in the state. Energy can be exist, but the problem is that if it's heavily doped, it can be exist like just normal, just conduction band, because conduction band definition is like 0 Kelvin is the lowest energy level that is not occupied with anything. So the conduction energy level can be changed, but the Fermi levels can be up in the conduction band that changed. So the problem is that it acts like a conductor, as we learned, because we can say conductor or semiconductor or like intrinsic, not intrinsic, that insulator we can define by energy band gap. But as we talk about the conductor, it can be act like a conductor if it's generated. If I mean, can we act like a semiconductor? Can be act like a degenerate, act like a conductor, which is the degenerated semiconductor. But as we focused on the carrier concentration before the midterm exam, we were talking about the concentration, but we should focus on the part of the velocity, which means we were learning about the current density, and current density means we can divide into two parts, which is one can be defined in carrier concentration, and one can be defined in mobility times the electric field, which means it's related with velocity. So we learned about the velocity, but there's a specific velocity we call drift velocity, but there's like the velocity is usually related with mobility, and the whole current of drift current is equals to the whole current and whole drift current and the electron drift current. So we learned that the current is equals to that, but the problem is that if we solve the equation, it can be changed into conductance. We can change into conductance meaning. And as we learned about it, we start to learn about the drift, before about telling about the scattering, as we learned about the drift velocity. The usually our professor said that it's same like when we are in the bus station, we are just walking around, but the state is just stay still the same. If we made a mean value of it, it means just same, just staying in the zero state. So not the problem, I mean, so when the electron is just moving around through it because of the electric field or something, there can be a scattering, and there's like different scattering type. We learned about the three type of scattering, but as we talk about it, there's more stages, professor said, but we learned about the scattering, which is related to just ionized stuff into like, well, force, which is like a, donor. And yeah, and we talk about that, and ionized acceptor and donor, which is that can make like electrons or hole can be make like a scattering. And we learned about the lattice scattering, which is related with just like a vibration of just, there's like in semiconductor we usually talk about the silicon, and silicon can be vibrated by the energy, which is related with the temperature energy. So it can be vibrated and it can affect to the electron that can be just going around. It can makes that electron scattering. And the last one is that we learned about the surface roughness of the scattering, because if we think about just the flat, if we just think about the semiconductor, we are thinking about just flat and just clean, just neat, just flat, just that kind of thing. But it's actually the surface is not that clean or like not, so it's like really roughness. So, but we talk about that, and if we want to know about the scattering of like times, it was like the time was like the was about the time, but we call it mean free time. And but if we want to add the time a lot in and make a mean value, but the problem is that if certain time is not like certain time is really high, it's not that have like critical meaning about it. So we use the harmonic mean value. Yeah, harmonic value. So we use that, and as we talk about that kind of time, but we related it into mobility. So there's like we are talking about the log scale between the temperature and the mobility in log scale. So we talk about the graph and the scattering, how it move, and the high field. And as we talk about that, we were talking about the after that we talk about the current, about the drip current, but there's like a different current saying about the diffusion current. And diffusion current is actually related with the difference of the concentration, because if it's there's like if it's in certain part, if it's there's like high concentration about certain carrier, it can move it fast, and it means that diffusion current can be really fast. And we divide into the diffusion coefficient that is really important to us, and it's related with the velocity and the length of it. So we talk about diffusion current, and we add this thing into one part. So the current density is related with diffusion current and diffusion current and the drift current, which is we can divide into hole and electron, hole and electron, like that. So we talk about that, and that's for all for talking about the current density. Thank you.